If we want to make AI systems safe, it can kind of help to understand how neural networks develop, where the structure inside the neural networks come from. This is the dream of science of deep learning, and singular learning theory is just one specific kind of approach or set of ideas that says, look, degeneracy might be kind of key to this process, and then we can bring in tools from algebraic geometry and other parts of mathematics to be able to kind of analyze that degeneracy in neural networks and use this for applications for understanding structure in networks or controlling it. Degeneracies basically means you have in your parameter space different parameters that implement the same function or achieve the same loss, depending on exactly which definition you want to use. These degeneracies show up all the time in neural networks. So classical statistical theories that assume away these degeneracies are not going to be able to tell us about learning in these neural networks. And in terms of safety specifically, I guess we want to know about structures like, is there going to be a sort of internal goal in this neural network? If there is that goal, is it going to be aligned? We might want to have control over those exact structures. It could be control, or we could also just want to be able to predict. If I have a certain training setup, do I have to worry about an internal goal arising at all? And if I had a better understanding of what the different inputs to training, like data and environment and architecture, how those influence the kinds of structures you're going to get inside a network, I might be able to say, yeah, this training setup is safe. I don't have to worry about any emergent optimizers coming out of that. Singular learning theory has some results that tell us how Bayesian inference should behave in neural networks. For example, it can help us understand things like inductive biases of an architecture in this sort of idealized case of Bayesian inference. It can also be used to try to develop new tools for mechanistic interpretability. If you can understand kind of where structure comes from in the learning process, then you can use this as a hypothesis for where sort of circuits and features might come from in deep learning from an interpretability perspective. And sometimes people call this developmental interpretability because you're focusing on kind of the learning process and where these structures come from over training. More recently, people are kind of pioneering techniques to apply singular learning theory to controlling the kinds of structures you get in your neural network, the kind of mechanisms, using an approach that's been called patterning, which is kind of about trying to understand, instead of for this structure, where did it come from in the data, it's sort of saying, if I want this structure, what data should I use to train on? So it gives you kind of curriculum for learning. And then you can have more control over the precise sort of structure that you end up with. Sumio Watanabe brought together ideas from all over pure mathematics, including especially algebraic geometry and stochastic processes. However, I don't think that you really need to have an extremely deep maths background to understand the essence of singular learning theory and what it tells us sort of for deep learning. And so one of the things that we're trying to do here at Iliad in the intensive singular learning theory module is really isolate the kind of core of singular learning theory with as little mathematical prerequisites as possible. We start with sort of an overview lecture, what makes neural networks singular and why this might be important for learning, and some of the kind of empirical evidence around this that we've been sort of developing as a research community over the last few years. But then after that lecture, we really think the best way to approach this is to get you doing exercises. And so the rest of the day is dedicated to a set of lecture notes that we've written that distills singular learning theory down to very simple, concrete examples where we have as little prerequisites as possible. And then you work through these exercises sort of one after another. And by the end of the day, you've done everything from understanding what is degeneracy to understanding this key quantity, the local learning coefficient, which is this central kind of mathematical object, to understanding the main result of singular learning theory, Watanabe's free energy expansion. Understanding deep learning and neural networks and how they learn is one of the most challenging but also important problems that is facing the field of science today, because these networks are so impactful in practice and could determine like how the future goes for the entire world. Singular learning theory is an incredibly exciting approach to doing this. It lets me sort of solve fun maths problems and run experiments and be a scientist while also having potentially a big impact.